Chapter 26 is our electric potential chapter. Now, this page of notes, this first page, will talk only conceptually about electric potential, which, just so we know right off the bat, as it says here, is voltage. Electric potential, and please make sure you get this into your notes, is the same thing as voltage. So conceptually, the way I want you to think of voltage, I want you to think of voltage as electric field or electric field energy pressure. And it's an electric field pressure. Voltage is a pressure that pushes a positive Q from a high voltage to a low voltage. So we can think of this in the same way that we would think of air pressure, pushing an air molecule from high pressure to low pressure. So you don't need to put this into your notes, but let's just make a box here and consider that this is going to be a high pressure box. And we're going to put a window, circular window or diaphragm in this box, but we're going to say that has high pressure, so we've pumped it up, like pumping up a tire, right? We've put a lot of pressure into the tire. Let's say we join it with another box, and this is going to be our low pressure box. So I'm going to color code it here. So if red is my high pressure box and blue is my low pressure box, if I open that window or break that diaphragm, the air is going to whoosh from the high pressure to the low pressure, just like if you puncture your tire, the air whooshes out of the tire from that high pressure inside of the tire to the lower pressure outside of the tire. So you don't need to put that in, but I just wanted to make sure we are firmly rooted in that conceptually voltage is like this energy pressure. So you want to think of voltage as pressure. All right, let's erase that and clean this up. All right, well, we've seen the word potential in physics before, as it says here, potential energy. So we have to be really careful with the language and the nomenclature that's in a problem, because if the language they use is electric potential energy, that's joules. That is not volts. So that's joules of energy as we've always used. If they say, and the language is just electric potential, then they mean voltage, and that's volts, and that's the energy pressure that we just talked about. Well, these two concepts are very closely related. So we're going to mathematically remind ourselves of what we did with potential energy in physics, and then on our next page, our next lesson of notes, we'll talk about the mathematical definition of voltage. So the rest of this page of notes is really just, I hope, review for you, reminding you of what we did with electric potential energy, and we're going to relate it both to gravity and electrostatics because the mathematical structure for both gravity and electrostatics is identical. So mathematical structure is identical at different variables, but let's remind ourselves of what was going on for potential energy. Well, first, gravity. Potential energy, by definition, right, is equal to negative the work done by the restoring force. Well, gravity is going to be the restoring force, so the gravity G, negative 9.8, and by the way, that's our field vector for gravity, just like the electric field is our field vector here in electrostatics. And for this example, we're going to talk about increasing potential energy. So when we increase the gravitational potential energy, we lift the object up in the air. So we go from some initial down here to some final up here. So we're moving the particle in an upward direction. Gravity is downward. Gravity, of course, does not shut off when we lift the object. So when we're calculating the work done by gravity, we are calculating F dot delta y, and of course, since gravity doesn't shut off, we get cosine of 180 when we lift the object. We have mg, our delta y in this case is h. The work done by gravity is negative mgh. When we use our definition for potential energy, by definition, the change in potential energy equals negative the work done. Hopefully this is ringing bells. We introduce this additional negative, which is contrived, it's put in there on purpose, to make the change in potential energy positive, when we lift the object up. So that is our MGH that we had back in mechanics. We had a lot of, kinetic plus potential initial equals kinetic plus potential final. We did a lot of those problems. And we saw that our potential energy function was mgy, just one of any, in a generic sense, the mgh becomes an mgy. Well, we have the identical situation with electrostatics. So the language is all going to be the same, so I'm not going to spend a lot of time just repeating exactly, but initial final, we get the cosine of 180 because the electric field does not shut off when we lift it. The force is QE, the delta Y is now D. So the work done by the electric field, right? The work done by the electric field, negative QED, so by definition, negative, the change in the work, the two negatives give us a positive, so there's a positive change in potential energy for a positively charged particle as we lift it upward against the electric field. The potential energy now has an expression QED, which, again, same mathematical structure as mgy, and as it says here, these two equations only are good if F is constant because we used F dot delta Y. If the force is not constant, which it doesn't have to be a constant electric field or a constant gravitational force, we would have used integral F dot ds, but mathematically we would have done the same thing. We just would have had a different expression for our W and our work done by the fields. So please make sure you get all of these annotations. Let me erase it here and clean up my addition. So pause the video, get all of your annotations in here, and we will look at a mathematical definition of voltage.